In this lesson, we shall focus on COS 1501, Introduction to Theoretical Computer Science. And we begin by looking at question 4.2. Given the incomplete table below for the binary operation, and we have looked at this particular table before, and we understood that B is the identity. Right, so if B is the identity, there are a couple of things that remain very important. So A star B will be A, and that became C, because B is the identity, B star B becomes exactly that. Okay, and also we're told that C star C is actually B. Okay, good. And so now we actually obviously looked at the fact that C star B itself, B being the identity, gives us C there. Okay, but also B star A would actually be A, and also B star C would be C. Why would B star C be C? It would be C because B is the identity. It does not change the A, it does not change the C, but also B being the identity combined with itself under the binary operation becomes the same identity there. And so obviously we realized that this would then be A there. And obviously looking at the symmetry, B, A, and we have our C there, etc., etc. Okay. Okay, yeah, well, I was just doing this table thing, completing the table there like we did before. But can A star C in brackets star B and A star in brackets C star B be used in a counterexample to prove that the operation is not associative? Motivate your answer. Let us check these first here. So we're going to do A star C in parentheses star B. We suppose that it is equal to A star C star B. Right, what according to this table is A star C? Right, so we're able to see that A star C. Right, so if we are to look at exactly that, A star C gives us exactly C star B. Okay, and this is A times C star B would give us what? Would give us exactly a C, right? Why would this be the case? Because B is the identity in the previous question. We're told that. C star B, right? So that C star B becomes exactly what? Right, C star B becomes C because B is the identity. Being the identity is like saying 3 times 1. It will just be 3. Why? Because 1 is called the multiplicative. In this case, it is called the multiplicative identity. It is called the multiplicative identity. The B is the identity, so that 3 times 1 becomes 3. So C star B becomes exactly C. Right. And if we look at exactly A star C, it would actually be C there, this way. Right. And so can these be used as a counterexample? Well, it is producing C equals C, which is true. It is producing the truth. And so the answer to this is no. It cannot be used. Right, no, it cannot. It cannot be used. Why? It cannot be used as a counterexample. It cannot be used as a counterexample. Why can it be used as a counterexample? Right, cannot be used as a counterexample because it is actually giving a true equation. But if ever it would make the left not to be equal to the right, we could say that. So in this case, it cannot indeed be used there as a counterexample. Yes,
Okay.
please.
Can I ask a question?
Yes, you're welcome. Yes, yes.
Okay, why is C star A and A star C not the same thing? What makes it different? That's the only thing that's
Okay,
confusing me at this
yes, well
point.
done, well done, well done, because it is not commutative. Okay.
Okay, so because it's not commutative, but how do I decide like which one would be C then and which
Okay,
one
okay,
would
I
be
see, I
A?
see. Well done, well done, well done, well done. Because in the previous question, I hear you there. In the previous question, we said that star is not commutative, right? But also we were told that it is a binary operation. So a binary
Yes.
operation means it is a closed operation. What does it mean it is a closed operation? It is an operation such that when you combine any pair of elements, you get a result that is in the set. So the set we are studying is a set that has these particular elements A, B, and C, but it has also the operation there. Meaning, okay, in each row we must get all the elements here. Okay, we must get
Okay.
all the elements there in the set because the set is closed. So it can't be an element that is outside the set. So now, for instance, as you're saying, so because we were given another hint in this case that B is the identity element. B being the identity, meaning that if you combine, it's like a 1, as I said, 3 times 1 gives us 3. B is the identity, meaning that it vanishes when it is multiplied with another element. So because 1 vanishes when it's multiplied with 3, and we get 3. B being the identity, so A star B will just be A. Right. And so now when you get A star C, right, so if you look at A star C, it would have to be another element there because we have already got the B and the A. Right, and in this case, it becomes obviously exactly a C because you already have the B and the A. But also C star A would become what? Obviously, because you know that C star B would become what? Because B is the identity, it will therefore just become a C there. Okay, and also we note that these particular elements are such that there is symmetry in this particular sense. I will speak about the table symmetry, right? And so now what you then have as well is that B being the identity element, what it does, it fixes all other elements, meaning a B star C, for instance, would fix C. And so now we have this particular order of the elements there. Meaning you can see the order, the C is actually reflected as well there. And now in every, because if this is a binary operation that is not commutative, we can therefore be in a position to see that C star A would have to potentially yield an element that is not amongst these here. And so it will potentially be A. So A star C being C, because there's no other C in this row, and also C star A being A there. And so B star A would obviously be just A because B is the identity. Okay, so these should be sort of, but now if you look at the order of these here, across this particular diagonal, you can see that obviously A appears in the same position, B appears in a similar position on either side, C also appears in a similar position on the other side. In the same way, we are able to see that A appears in a similar position, giving us a symmetry. So you have B, 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 and here you have C, A, C, and obviously you are able to see that level of symmetry as well with the C there. And obviously now these are some of the properties. Some of these binary operations produce certain structures, and the structures have special names like what we call groups and rings. Rings, and some structures we call modules. Okay, so obviously each structure is its own given properties. Some are called monoid structures. However, obviously in this case, we actually were given this, and there were two hints. That is, it's not commutative. But if it were commutative, it would mean that whenever we see A star C, the result will be the same as C star A. But obviously here it is not commutative, and therefore it has to be different.
Okay,
Right.
so if I understand, when it times is with B, it's like timesing with 1. So that's
Yes,
why then it's not, the commutative thing doesn't really matter. But when
yes,
it comes to C times A, then it's commutative, so they switch around basically, because they
yes,
can't be the same answer. And
yes.
then what I understand so far, so A, B, and C, because it's a closed operation, must be in the rows,
In the
or
rows,
each
yes.
row,
For each
but
row, yes.
not in the columns. It doesn't matter
Yes.
in the
In
columns.
the columns, it must
Okay.
be, yeah, it matters in the rows. Yes, it matters in the
Okay.
rows. Well done,
Now
well
I'm
done.
with
Yes,
you.
yes, well done. Thank you so much. It matters in the rows because you're able to see, we follow the rows there, most importantly. Okay, but thank you so much for noting that one. Okay, I'm sure we shall do a lot of examples on this. Thank you. Thank you again there for noting that problem there. Okay, the next thing we shall discuss is the notion of what we call the truth statements and false statements and tautologies, and what we call mathematical, right? And there's something called mathematical logic, or what we call propositional logic, right? Propositional logic. For each of the following statements, if you think the statement is true, circle true, else circle false, okay? Or F for false, okay? Right, so let us look at these here. In here, we are looking at the Roman figure 1 in question 5.1 part A. And now we are saying not P implies Q is logical equivalent to not Q implies P. Right, so we're asking the question, is this true or false? So the couple of rules we need here, there's something that the logical equivalence of these relate to something we call the contrapositive. Right, there's a rule. Okay, this one is a rule. What you call the contrapositive, or what you call contraposition. Right, contraposition. So now, in view of contraposition, you would say P implies Q is logical equivalent to not Q implies not P. Right, and this is the contrapositive. And so we shall use that rule here, which produces the equivalence in this case, or what you call logical equivalence. So now we continue then to investigate this and see exactly what we have. So let us check this question. So now we're going to take this one. So in this case, if we use a different color, suppose we use blue, so we have not P, the examiner changed from the P implies Q usual statement to actually not Q implies P. And so we must say not, we must say not. We must say not their conclusion. So would say your not Q implies not P. And so now we would then say it implies not what is the premise. And obviously viewing these as our premise, so it will be not P. And so this is the same as not Q is logical equivalent to, so this is, we say it is logically equivalent. Right, logical equivalent. So now we have this, but not P is just P. There it is. So this one is the contrapositive, or what we call the contraposition. Right, and by dint of this, we are able to see this as true. But it's not the only way to reason this out. There are a couple of ways to reason this out. One of the methods we use is the following here. We use the disjunction. Right, we know that, so we can start from the left. So now starting from the left, or what to check. So to check, you can write not P implies Q. And now it is logical equivalent to not Q implies P. And then now you take the following. The implication is changed to not P or not Q. And therefore it is not Q or P, because P implies Q is not P or Q. So these are the same a logical equivalent. Right, so that in this case we have not P, which is just P implies obviously not Q is logical equivalent to Q or P this way. Right, so obviously I meant here we need to have not because it must be not the premise or the conclusion. So in this case, you'd have not the premise or the conclusion. So it's going to be exactly this. But we understand and we most certainly agree, but vehemently, that P or Q is commutative, this property giving us P or Q. So indeed, this is the truth. So we actually uncircle the correct one. And the correct one is the truth symbol there. And we practice with the next one. Right, the next one is the second Raman figure. And now we want to investigate this one to check is it true or false. Once again, we're going to, because this is clearly the, we try to take a side and simplify and produce another side. So what we're going to do is we're going to take not, we're going to take P or, right, P or not Q. Right, we're going to take a P or not Q and R. Right, we want to compare with P or not Q and R. So we manipulate these and see what we can get with the manipulation. Okay, right, what exactly do we get with the manipulation here? So we can use something called the distributive law. Right, what we call the distributive law. What is the distributive law? The distributive law in any order says that if you have P and Q or R is logical equivalent to P and Q or P and R. Okay, right, so now we're going to use it, but this one is going to be distribution from the right hand side. This one is distribution from the left of the of this particular expression. So in this case it's going to become the following. It's going to be P and R or, right, not Q and R, like so. Right, and so we are able to exactly get this. And so now, if we check this very, very carefully, how is it therefore different from this here? Right, so we can write it as P or not Q and P or R. Okay, we pause to check, are these equal to each other or not? Right, are they at all different or not? Right, by looking at these very carefully, we're able to see that whenever the and appears in the middle, there is or and there is and there. And also we are able to see that these are three symbols. And we're able to see that here there is not Q and R. And by dint of this observation, we're able to see the falsehood of this particular expression and the fact that we have used the distributive law and these are very, very different from each other. Right, and so, but there's more we're gonna obviously do to explore these kinds of relations. Right, but this would be false there. Let's look at the third Roman figure. Let's look at the third Roman figure. This one here. Now, in the third Roman figure, not P and not R, considering the left-hand side of the equivalence relation. And this is exactly the same as not R or not P. Okay, now let us reason this together and see what we have here. So this would be the same as exactly the following. Right, so we can obviously be in a position to expand this. Okay, let's look at the left. So because we know by the law called De Morgan's law, right? De Morgan's law. So now we're going to write De Morgan. Right, we're going to write De Morgan's law. Right, so De Morgan's law. Or what you call the negation. Let's call it the negation, more precisely. Right, so now we can say the negation of P and R is not P or not R. Okay, not P or R is not P and not R. Right. So now, if these two laws contain the negation of the disjunction and the conjunction, you would have the distribution here. So this one is going to be not P. Okay, the end changes to OR, and we have not R. Okay, and then we compare with this one, R or not P. Right, so now what is not R? Not R is just R. So this one is not P, but not R is just R. So we have R like this, and it is a logical equivalent to not R or not P. Not R or not P. So that then in the end, we have these. But these are exactly the same because what we have here is not P or R is logical equivalent to not. And then this one is not P or R. Okay. So these are the left and the right are exactly, are pretty much exactly the same. In particular, they're exactly the same. And therefore, this is a true statement. So which means, therefore, here we're going to encircle the truth value true. Right, and so very, very easy questions on statements and what we call prepositional logic. And we move to the next question. I want us to look at the next question on prepositional logic and try to make sense of it. We move forward. Right, so now this one is way too easy and very interesting. We need to complete the truth table for the following compound statement. Hint, complete the highlighted column last. So you're going to complete this one last because it has all the symbols we need. But now let us look at this one here, which has 1, 2, 3. You're right. 1, 2, 3, 4, 5, 6, 7, 8 rows there. Not P would be. Okay. P is has 1, 2, 3, 4 true symbols. And 1, 2, 3, 4 false symbols. And we take the negation of this. If you negate true, you get a false. 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 You negate false, you get a true. You get a true, you get a true, you get a true. Right, so we negated everything in the column P. And then here we focus on the column Q and we negate that. And if we negate these, then we negate true, we get false. We negate false, we get true. We negate these, we get false. We negate false, you get true. You negate true, you get false. You negate false, you get true. You negate true, you get false. You negate false, you get true. Okay, so now we negated every truth value there, every truthhood and falsehood in the column for R, and this is what we got. And then right now we come to the implication row there, and we take note of the following here. that if ever we look at P implies Q, it is the same as not Q, not P or Q. Okay, I want to discuss this here. Very briefly, not P. Right, so I'm saying P implies Q, because we're going to be using this a lot, is the same as not P or Q. So now you'd have exactly the following. You'd have exactly the following. So that then in the end, what do we have here? Okay, I want us to discuss this in detail. So to understand this very well, I want us to look at the PQ, true, true, false, false, and then true, false, true, false. Right, so that in the end, then you have not P, not P, right, which is going to be false, false, true, true. Okay, that would be the not P. Okay, there's something I'm trying to discuss here. The point I'm driving towards with this little table, because if you can understand the small one, then you can be able to do the big one. Right, so now we're going to do not P or Q. Right, so not P or Q, we're going to focus on the first, not P or Q, these two here. Right, not P or Q. So now in mathematics, when you say, for instance, false or true, you get true. Right, and so false or false, you get false. True or true, you get true. False or true, you get true. I want us to look at these and ponder on this very carefully. There's more analysis that we need to understand here. So now we can we want to proceed with this, right? So we proceed as follows. And now there's more we're going to discuss in this case. Right. So now let us look at the following. So we are then saying here, this one is the same as P implies Q. So P implies Q is the same as true, false, is the same as this. So true, true. So we analyze together P and Q. This is the true row, true, 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 false. Okay, right. So now, if P and Q are both true, then this is true. But if P is true and Q is false, if the conclusion is false, then indeed this is false. But also if here you have a situation. So if the premise is true, then this is false. But if the premise is true and the conclusion is false, then this is false. Right, and so if you have that the premise is false, then the conclusion in this case becomes true. Right, if the premise is false. Now, we're analyzing this because if P is false, then it doesn't matter whether the conclusion is true or false, the result will be true. So in other words, we're saying P implies Q becomes true whenever the premise is false. Right. But now we are able to see, so that when we are sure of when a premise is false, this is true. Okay, let us look at the following. So now we want to complete this with great ease and simplicity. Right, want to actually complete this with great simplicity. Let us look at the following here. So what then we will do is to analyze this table very, very carefully and see that whenever you have, so we're going to do this one last, but we're going to actually say not P implies Q. So this is not P, and then we have Q there. So we understand that whenever you have the premise is false, it will always be true. And so now we are able to see that all these here are false, right? And therefore it means that this is going to be, it doesn't matter about Q. Whether it is true or false, then this is going to be true. So we're going to put true here, you're going to put true there, you're going to put true there, you're going to put true there. Okay. Now, whenever this is true, if ever the premise is true, then you need to be careful because it can be either true or false. But now it depends on this is true, but if the conclusion is false, then it becomes false. You need to check. Right, and so here they are both true, so you're going to have true. Okay, here they are both true, you're going to have true. Because if they're both true, then you have true. And then here we have here the P and the Q. The Q is false. Right, if the Q is false, then you have a false. So you have this one here and this. So the minute then you have that the Q is false, right, and therefore, but there you have true, false, it becomes false, right? So, and then you also have the true, false, it becomes false. Now, okay, so we are starting this table, but very, very carefully. Let us reason this out, so and make sure we understand what is happening, because this is very, very important for us. So now we will proceed as follows, right? So we'll proceed as follows. We will proceed as follows. Right, we will proceed as follows. Okay, right, I wanted us to take a look at this and make sure we obviously understand this very well. Right, make sure we understand this very, very well. Right, and make sure we understand this very, very well. Okay, there's something I want us to analyze here and be very, very careful about, and make sure that we understand exactly what is happening. Right, and make sure we understand what exactly is happening there. What is happening there? Okay, right, we are moving on, but now I'm actually trying to make sure that we are very, very careful in the way we analyze this particular truth table, and we to make sure. Okay, pausing because there's more we're going to do right now. So let's look at what we have got and make sure we understand every single bit of thing, every single bit of thing. Okay, I want to reinforce the fact that whenever you have true, true, then you have true. Okay, I'll tell you why I'm emphasizing this. Whenever you have false, true, right, false, true, you have true. Whenever you have true, false, you have false. Whenever you have true, true, you have true. Okay, now this is very important because you shall be doing even biconditional and other things. Okay, so take note of these because you're going to be using this little table to complete the big one. Right, and so now with this in mind, we actually note, therefore, that once again, whenever both of the premises are false, then this is surely true. But whenever the premise is they are both true, it's true, and whenever the premise is true and the conclusion is false, it is false there. Okay, good. Right. So let's move on to this one. Now we're gonna take the P implies Q or R, right? So we're gonna have this one here, and make sure that we understand this very well. Okay. Right, we continue with our analysis of this. Let us make sure that we understand what is happening. Okay, pay particular attention to the table because there's more we shall play around with it, but I want to make it much more understandable, and this is the wish. I want to make it more and more understandable. So it is something, therefore, that is very important. We are seeking to make sure that it is very understandable. Very, very understandable. So let us pay attention to this. Right, so if we have that this is the case, yeah, we have true false because we have seen already that true becomes true in the implication, true false becomes false, false true becomes true, false become false. Right, so we actually obviously are satisfied with that part. Now I want us to look at this one here. So if we look at these, what then are we able to note? We are going to take this one here. We're going to take this one there. We're going to take this one here. We're going to take this one there. So that in the end, whenever you say this or this, so true or true, we can see the truth because they are both true. Right, and so now we reason these out together. We reason these out together. So now, if we then say, for example, true or false, right, we have true or false, true or false. So we'll get to that point. I'll get to that point. Right. I'll get to that point. There's more I want to say there. Right. Whenever you say true or false, we take the truth. Whenever you have true or true, the truth. True or false, true. Right? So take note of that. Whenever you have true or true, yeah, true or true, true. So, okay, I want us to mention the following to make sure that we're on the same page with this. Let us look at the following table. I want us to draw a little table like this. Is the reason why I want to make sure that this is not confusing. Right, so you have true, true. You have true, false. False, true. False, false. Okay. Okay, now I want us to look at, okay, we're gonna go back to the table, but there's a study I want us to make here. Okay, we can do P and Q. And then we're gonna do P or Q. Yeah, P or Q, both of them. Okay, there's something I want to clarify here so that we can make sure that we get everything right, that we understand well. Okay, so if you look at the end, true and true becomes true, true and false becomes false. Okay, false and true becomes false, false, false becomes false. False and false becomes false. And then now when you do P true or true, it becomes true. Okay, I want us to fix that. True or false becomes true. False or true becomes true. False or false becomes false. Okay, I want to check that we've been very consistent in this little table here. That's what I want to verify. Because obviously we have two truth values, two true and then false, false. True, false, true, false. We negated the P and we have false, false, true, true. And then now we take the not Q, not P or Q. True or true, we have the truth. And now we come here. Right, false or false, we have false. True or true, we have true. False or true, right? And obviously we have the true there. We have the true there. Okay, good. That is okay. I'm just verifying that everything is most certainly in the right order. In the right order. Okay. Just verifying that everything is in the right order. So that now when you have this, you would have a true, false, true, true. True, false, true, true. Okay, so 100%. So the table is 100%. Okay, 100% correct. Just verifying there to make sure that we make no mistakes here. Okay, in the big table. Now, let us come to this one. So now I was saying we take this one, for example, using the same rules there. So we have this one here, which is true, or, okay, because we take this one, or R is this one. So if you then say true or false, we get a true, false or true, true, false or false, we get false, like that. Okay, so now we are done with this one, and then we come to, okay, this one we're going to do at the end. Hint, to complete the highlighted column last. Okay, this one, because there's a lot of things to do. Okay, now we're going to do this one. Now we're going to do this particular column. So in this column, we're going to take a not R implies Q. Not R implies Q. So you must remember that. So to make sure you don't get confused, I want us to mark these a little bit so that we don't forget and we possibly, do mistakes, etc. So we want to make sure we do correct things. Right. So not R, Q. These two. Let's start the game. But to start the game, we know very well that with the implication, it's easy to start with the false premise, because the false premise will always be true. So, in other words, false R. So you're going to do a false R, false R, false R, false R. There's no reasoning there. So this one will just be true. Doesn't matter what the Q is, but as long as this one is false, whether this is true or false, it will just be true. So in other words, if we do this, then we're going to do this one. It's going to be true, 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 true. So true, 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 true. Next. Now, next, also we can have the truth. The truth where we have both true, truth values true, right? So you have true, and the Q is true. So this one is going to be also true. I'm putting a star there. So let's put a true there. So we're done with that one. This is true, but true, false is false. So we're going to do true, false is false. And then now, so we are done with that one. True, false is false. So this one is true, true with Q. It's true, yeah, true, true, it's true, yeah. Okay. And then now we come to this one also. The not R implies not implies Q. Right. So now we have true, false. But we see true, false becomes false. So true, false becomes false. In other words, the truth does not imply falsehood. Okay, right, so we get to this. Now we are done with this particular column here, and let us look at this one. Okay, now we already have the not P implies Q, but it is such that it's not P implies Q and what? Or not, right, OP, yeah, OP. So we have exactly that, OP, OP, OP. Okay, let us continue. So this one, not R implies Q, but we must combine that with OP. OP is this one here. So we're going to just do this one with the first. So now we say true or true, true. Right, true or true. So this one, your true. Okay, there are three truths. And here, this one is four true. So you have that. So now there's a false or true, true. Okay, this one, true, true or false, true. Okay, let us continue. True or false, true. True or false, true. False or false, false. Right, so we continue. We continue. We continue. We continue. If then you then say, now we come to the last one. So the last column is going to be this, but this one is going to be exactly the not P implies Q or R, which is this one. And it implies, which one? It implies this one here. The not R implies Q or P. So now we're going to focus on the following. I'm going to mark them green. I'm going to put a star on this one. So we're going to deal with this one here. Going to deal with this one. Okay, going to deal with this one, which is the not P implies Q or R, but also going to deal with this one, not R implies Q or P. We have this. So now, let's come to this one. But which one do we start with? That's the thing. So we need to start with P implies Q. We start with P, then Q, yeah? So we start with which one? Okay, good, because now we start with this one that is on the left. Not P implies Q or R. It implies not R implies Q or P. So it's this or this. So now you have true, true, right? Because now, okay, this is easy. Because now if you have that this is false, if the premise is false, then you have the truth. You have the truth. So this is false here. We don't have a lot of the false here. So this would be true, yeah? And then now we come to this one. Okay, but there are too many true there. Okay, but they're also easy, this true, because if it's true, then it's true. But if it's false, then it's false. Right, we start. So this is true, then it's true. True, then it's true. right? True, true, then it's true. 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 Aha! Very wonderful. This is called a tautology. Tautology. Because it's true always. True always. So now we come to the, because we have seen that this is true, then we can answer the subsequent questions that follow as a consequence of what is next. And let us reason then very, very carefully and make sure we understand the next thing. Right. Is the expression in a tautology a contradiction or neither? Like I said already, we can actually with so much confidence say it's a tautology. Right, so a tautology is a statement that is true, always. Right, and so it is true always. Otherwise, it is called a contradiction. If it's not a tautology, then it's a contradiction. Now, let us check more problems and practice more. More problems and practice more. And more problems and practice more. Right. More problems and practice more. More problems and practice more. Okay, let's check. Okay, now in 5.2, we are doing more investigations, but also we are trying to understand this module more and more. But we are spending time looking at statements more. For all z, right, for all x elements of z, right, if we have the 2x plus 3 is greater than 0, or 3x minus 2 is less than 0, is the given statement true? Justify your answer. Let us look at these and reason together. Is this true or false? Right, so we reason these, and the marks are only 2, so we actually obviously are able to look at that very, very carefully. Let us reason together through these particular questions. So we start for all x element of z. Okay, 2x plus 3 is bigger than 0. 3x minus 2 is less than 0. Right, so we can reason this out. There are many ways to do it, of course. We start by saying that this statement is false. The statement is false if and only if 2x plus 3, right, is negative and and 3x minus 2 is positive. Right, so the statement is false if x is, if the 2x plus 3 is negative and 3x minus 2 is what? Is positive. Okay, this would mean that 2x is smaller than minus 3 and 3x is bigger than 2. X is less than minus 3 out of 2. And x is bigger than 2 out of 3. Okay, this is the case since Since x cannot be less than, since x cannot be less than minus 3 over 2 and greater than 2 out of 3. Right, so we're then saying this statement is true if and only if this, because if ever x, let's look at the number line here, negative 3 out of 2, first we put the negative numbers and we put the positive numbers on the right. We are looking at the case that x is less than minus 3 over 2. There is a variable x that is smaller than negative 3 over 2. Yet the same variable is bigger than 2/3. And so we argue, therefore, that this statement here obviously is false if and only if this is the case. Because if you then take this and that, they cannot be both true. They cannot be both true. Because they disagree. This one goes to the left. X is negative here. And here x is positive. X is positive. X is negative and x is positive. Since x cannot be less than minus 3 over 2, since x cannot be less than minus 3 over 2 and greater than 2/3. So x cannot be negative and be positive at the same time. So this, therefore, obviously means these two statements cannot be true simultaneously. Because of that, we'll then be in a position to then say this statement is false if that is the case. It is false if that is the case. So now, obviously, you need to reason that out and process this and check if it is obviously true or not. So you'd say, we then actually say that the statement is true. We therefore see that the statement is what? The statement is true. Because we have already said the statement is false if we change the greater than to a less than. And if we alter these symbols here. We altered them, this one to less than and this one to greater than, and it produced statements that were opposites because we saw an x that is negative and then positive at this simultaneously, and this is false. So x cannot be less than minus 3 over 2 and greater than 2/3 simultaneously. It can't be simultaneously true. And what we then were able to observe is that the statement given with the greater than first and the less than second, obviously with an or is true. What is this? I want us to spend a minute or so discussing the significance of what we've done, because what we've done is consistent with the negation of this. So if you take the negation of this, let's take the negation of this, yeah? Let's take the negation step by step. Let's take the negation. So we negate 2x plus 3. We negate 2x plus 3 bigger than 0, or 3x minus 2 less than 0. We negate. Okay, this is the given one. We negate it. So if you take the negation, let us discuss the negation of this statement to get the truth of this. So the negation is going to be 2x plus 3 negative. And so you reverse this, it becomes the opposite of this. And obviously it would be this is greater, then you take the opposite of that, which is potentially less. And obviously, you can take that. And also, you take 3x minus 2 is bigger than 0. Yeah? So, and obviously, we took the negation and found that the negation itself is false. If we negated something, we negated x, and we got false, it means that the statement is true, because it is only true that whose negation is what? Is false. Because we took the negation of this and found that the negation is false, and therefore it means that we took the negation of a statement that was true to get false. Okay, Uma, thank you so much for joining us. It was awesome having this discussion. It's just 10 o'clock. Okay.
Okay.
Yeah,
Thank
good.
you.
Yeah, thank you so much. We shall save the recording. We keep in touch then for the next session. Okay, thank you so much.
Okay.
Goodbye and God bless.
Bye.
Thank you. Thanks. Goodbye.